Hello, everybody. Today we have chapter 9. This is all about gases. Our last chapter here of Unit 2. We are learning about the ideal gas law, kinetic molecular theory, and talking about the Maxwell-Boltzmann distribution of velocity. So, kind of keeping in trend with our last two chapters, we talked about solids, then liquids. Today we are talking about gases a bit. Now, gases, their main characteristic is that they expand to fill the volume of their container. The gas molecules themselves are pretty much just moving around randomly. They don't interact with each other very much. They have so much energy that they really don't care about the intermolecular forces between molecules. They're not held together in a particular shape. They're not held together inside, like held together in place like a solid is. Each molecule is moving independently and quickly around whatever its container happens to be. That container is like a balloon or a room or maybe like the atmosphere of a planet. Pressure is really important with gases. It is the measure of how much force is being exerted on like the walls of a container. A couple of quantities we talk about with gases are that pressure, the amount of force exerted on the walls of a container. We're going to measure that in a couple different quantities depending on the sort of problem. We have ATM for atmospheres, and pascals is kind of like the SI unit, right? The standard unit. And there's a couple other ones you might see as well, including millimeters Hg, which stands for millimeters of mercury, or torr. Okay? They're used for different types of pressure, like atmospheric pressure or the pressure applied by like an object, or like the blood pressure, water pressure, like different sort of fluid pressures. Each of these kind of has its own unit, and that's why there's so many of these different units here. We talk about volume, the amount of space matter takes up. Um, we measure this in liters. Temperature is the amount of heat in a system measured in Kelvin. Kelvin, if you remember, is just your temperature in Celsius plus 273. We use this intentionally for almost every single type of gas problem because when we're doing some math, we need all of our numbers to be positive. If our temperature is negative, which is like reasonable with Celsius or Fahrenheit to have a negative temperature, it could give us some weird answers, things like negative volume or something, which just doesn't really make sense. So we have to have positive numbers, which is why we use that absolute scale, the Kelvin scale. And last, we're going to talk about moles, of course, as we always do, the amount of stuff you have. To start, we have some definitions of temperature. So at the molecular level, for us, temperature is proportional to the average kinetic energy of the molecules in a system. Temperature is really just a measure of how fast all your particles are moving. So a single particle by itself, by definition, doesn't really have a temperature. Temperature is a macroscopic quantity, meaning you have to look at your entire system as a whole. All your particles, their average speeds, their average kinetic energies tell you what the temperature of something is. So you're looking at the average sort of particle, how fast it's moving in your sample. If the particles are moving faster on average, that means you have a higher temperature. If the particles are moving slower on average and have less kinetic energy, it means the temperature is lower. If your particles are not moving at all, you have now like frozen time, essentially, is what it would look like, and you have reached absolute zero temperature where there's absolutely no energy inside any of your molecules at all. So nothing would be moving. Okay. If I have a sample of gas, not all the molecules are moving at the same speed. So we talked about this a little bit with liquids as well. Any sort of thing where my particles are moving, some of them are moving really, really quickly. Some of them are bumping into each other and hardly moving at all. They're colliding in all sorts of different ways from behind. They have constructive collisions or destructive collisions, all these different types of collisions. And just because of that, they have some random speeds. And we usually represent that like in this picture here in the bottom right. You have these different size arrows just showing you how fast they're moving. The larger the arrow, the faster that particle happens to be moving. And this would be changing all the time. As the particles bounce off the walls, they move a little bit slower. As they bounce into each other from behind, they might move a little bit faster, right? But the idea is there's a distribution of velocities kind of showing you how fast your particles are all moving. Up here in this graph here, we'll use a lot. This is a Maxwell-Boltzmann distribution of velocities. Okay? You have essentially on the y-axis how many particles are moving at a certain speed or a certain energy in this case. And then on your x-axis, you're going to have either speed or energy or some sort of quantity measuring how fast your stuff's moving. Okay. At room temperature, you have this black distribution here. You can see the average energy would be at about the peak here, right around the peak. But you have particles moving extremely slowly. You have particles moving much faster. At a colder temperature, the average shifts to the left here. So this blue line, this colder, the average is less, but you still have particles moving slow and fast. The hot temperature will speed up the average, but you still have particles moving hardly at all, and some particles moving extremely fast. The molecules that are moving faster have more kinetic energy, and the temperature of a system is proportional to the average kinetic energy of the molecules in the system. Okay. As we're saying, we have a Maxwell-Boltzmann distribution of velocities over here. This one's talking about velocity specifically. Okay. The units look a little bit weird, but it's essentially like the same thing here. Your y-axis is how many of them are moving that fast, and your x-axis here is how fast they're moving. This is a weird looking unit, but this is just a way to talk about speed. So the higher the number, the faster they're moving. At 300 Kelvin, my average might be somewhere between 3 and 600 here. But at 1000 Kelvin, my average would probably be between 6 and 900, maybe even up a little bit higher, depending on where my average, maybe around 1000. It's a distribution of velocities of all particles at a certain temperature. As the temperature increases, the graph will shift to the right, because on average, more of the particles are moving faster. And if the temperature decreases, it'll shift towards the left. It'll kind of scrunch up because more particles are moving slower. Okay. Gases, on average, move faster when the temperature is higher. So the individual particles themselves move faster at a higher temperature. Temperature is the most important, the most basic thing that influences the speed of a gas. If the temperature goes up, the gases are going faster. Now there's some other things as well. The other one we'll talk about today a bit is size. The larger a molecule is, kind of the slower it's going to move. Small things tend to move much faster. Things with higher molar masses will move slower. Okay? With the same amount of force, a larger object's like harder to move. So you can probably throw, like, if you're decently coordinated, a baseball pretty fast, but you can't throw a bowling ball hardly at all. You can throw a baseball a lot faster than a bowling ball because it's smaller, it has less mass. Okay. We have a formula here that would be quite important for calculating the root mean square velocity of a particle. So we have this weird looking unit, VRMS, stands for velocity root mean squared. But that's just a really fancy way to say average velocity. Okay, so this is just how fast your average particle is moving. We'll talk about this a little bit in class, why they use this instead of just saying average velocity. It means something slightly different, but that's the idea. And that equals the square root of this entire quantity, 3 times R. R we'll talk about a bit later is the ideal gas constant, but it's just a number. So 3 and R are just numbers, times temperature, divided by capital M here is molar mass. And what this formula is saying is the velocity of particles increases. If temperature goes up, this number will get bigger. If molar mass goes up, since you're dividing by this number, velocity will get smaller. So the speed of a particle will go up if temperature goes up or if molar mass goes down because it's on the denominator. Right? If your molar mass goes down, you're dividing by a smaller number, which makes you have like a bigger number. Or if temperature goes up, you're just multiplying by a bigger number, so definitely goes up. Knowing that relationship is really important. There's all sorts of questions you're going to be asked about which particles are moving faster, bigger or smaller, or higher or lower temperature. This is the formula you use to do that. Realistically, this isn't something I'm going to have you solve as much as know the relationship between velocity, temperature, and molar mass. But I feel like it mostly makes sense if you think about that. Temperature going up makes it go faster, and then the larger something is, the slower it's going to go. So we want to rank the velocity of the following gases from slowest to fastest. Okay, so we have two different gases, so we need to compare those. We have helium. Helium is quite small. It weighs 4 AMUs. Xenon, I don't know exactly what it weighs, but it's way bigger, right? Xenon is a large. let's pull it up. Might as well. Okay, xenon is like 131. Okay, and then we have temperatures. We have helium that's going 500, helium that's going 700. We have xenon that's going 500 and 250. That was a dumb way to say it, but basically this is the temperature that gas is at. Okay, so we have a small gas at 500 Kelvin. We have a small gas at 700 Kelvin. We have a large molecule, xenon, at 500. We have xenon at 250. Okay, and it said we want to rank them from slowest to fastest. So first of all, we can look at the size of the atoms. Xenon is larger, so they should be moving slower than helium. So helium should be moving faster. But the second thing we have is the temperatures. The higher the temperature, the faster you're going. The lower the temperature, the slower you're going. The slowest temperature is 250, and it works out that that's the slowest, that's the larger molecule as well. So xenon, the large molecule at 250, the lowest temperature, is definitely number one. It's definitely the slowest gas. Okay, the next one, we have two things at 500, so they should be tied if they were the exact same molecule, but again, xenon is much larger than helium. So even though they're at the same temperature, this one will be number two. It's a larger molecule, it'll move slower. My two heliums here, the one at 500 will be next. And then 700 degrees Kelvin is the highest temperature with the smallest particle, has all the conditions to be the fastest molecule here. Okay. So you would have to do some calculations if I gave you like a xenon with like 1,000, for example. If I told you xenon that is moving 1,000, because this tells you it should be moving this would be like the fastest, but this tells you it's moving the slowest, then you would have to calculate. But in this problem, I designed it a specific way you didn't have to do any sort of calculations. And that's more like what I'd expect you to see. Okay, this leads into kinetic energy. Kinetic energy, you'll see it abbreviated either just capital K or capital KE is what I prefer to use, is the energy of motion. Kinetic energy can be calculated using this formula. Kinetic energy is equal to 1/2 mass times velocity squared. So this is how you calculate how much energy something has. The more mass it has, the more kinetic energy you have. The more velocity you have, the more kinetic energy you have. The thing to note is the velocity is actually squared, so velocity plays even more of a role than the mass. According to the formula, kinetic energy increases as mass increases. Kinetic energy increases exponentially as velocity increases. Doubling the mass of an object will double its kinetic energy. Doubling the velocity of an object will quadruple its kinetic energy. As temperature increases, the velocity of a particle increases. Because of this, the kinetic energy also increases. So when the temperature goes up, the kinetic energy goes up as well. Okay? The velocity, this v RMS, is kind of like the same as this v here. We would treat them the same way in this situation. The velocity goes up when the temperature goes up, and therefore the kinetic energy also increases. Temperature has a direct direct correlation to kinetic energy. If one goes up, the other goes up. If one goes down, the other goes down. Now, molar mass is actually a little bit different. If molar mass increases, if your particle gets bigger, or you're comparing a larger particle, the velocity does decrease. Okay? But the mass has increased. So if we kind of go back to our formula, when the mass goes down, the particle moves faster to correlate. So what actually is going to end up happening here is changing the mass isn't going to affect the kinetic energy at all. The kinetic energy was more complicated. I'll explain it here on the next slide, but it doesn't change as mass changes. So changing the molar mass, because if you make it smaller, it'll just move faster. If you make it bigger, it'll just move slower. They kind of like contradict each other a little bit. So molar mass, increasing that won't affect the energy at all. Okay, here's the math to kind of support that. The gas is now heavier if I increase the molar mass, so the kinetic energy should be bigger if we're just looking at this formula, kinetic energy. A bigger M should mean a bigger kinetic energy. But at the same time, the gas is now moving slower because of this formula. If I increase m, mass, in this formula, my answer for velocity will be slower. Okay, and the square root is going to kind of come into play here, right? We have a square root over here and a squared over here. Okay, so how it works out is if I divide the mass of something, or if I double the mass of something, the velocity will decrease by a factor of the square root of 2. And then in the next step, I'm going to square the square root of 2, so it's just going to be 2. And how it ends up is all just sort of canceling out. The velocity of the gas goes down, the mass goes up, it all cancels out. Changing the mass of something doesn't affect its kinetic energy. Okay, we could do a proof of like that using some numbers and stuff in class, but basically changing the mass doesn't do anything for the energy. Okay, which sample of gas below should have the greatest root mean square velocity? So which of these should be moving the fastest? Okay. Sample 1 has 1000 Kelvin as its temperature and a molar mass of 85. Okay, what we're going to do is plug that into velocity, RMS equals the square root of 3r. R is just 8.31 times temperature, 1000, over 85 is the molar mass. So you're just going to take these two numbers into the velocity root mean squared formula and plug them in. The 3 and the 8.31 are just constants, they'll just be numbers. You plug in the temperature to the top, the mass to the bottom, type this all into your calculator, and see what you get. Okay, so my calculator here, I'm going to do 3 times 8.31 times 1000, divide by 85, get my answer, flip it over, square root of that, I get 17.1. Okay, I'm just going to repeat that for my other two. My next sample, if I go back, has 1000 Kelvin and 60 molar mass. Okay, so I'm going to plug that in here. I have VRMS is the square root of the entire thing, 3 R's, 8.31, temperature 1000, divide by 60 molar mass. Okay, before I solve this, I'm expecting this one to be bigger because I'm dividing by a smaller number. Okay, the molar mass is smaller, so this should be faster. 3 times 8.31, 8.31 times 1000, divide by 60, square root, 20.4. Okay, so that one is moving faster. Now our last velocity is 3 times 8.31. Okay, my last temperature was 525 mass. So I'm not sure what's going to happen here. I made this number on the bottom smaller, but for that reason, this number should be bigger. But at the same time, I made the temperature smaller, so it should be smaller. So I'm going to have to do the math to see how this one works out. 3 times 8.31 times 500 divide by 25. Take the square root of it, and my velocity RMS is 22.3. When I do the math, my third sample is the fastest, has the highest root mean square velocity using that formula. Okay, so that's a little bit of math to kind of start with. This is called kinetic molecular theory, looking at how fast gases move and what causes them to move faster. Increasing the temperature causes them to move faster. Decreasing the molar mass causes them to move faster. Increasing the temperature increases the kinetic energy. Increasing the mass does not affect the kinetic energy. So kind of knowing how those things sort of work is pretty important. Now we're going to go into more traditional gas stuff, more like what you would care about in like honors chem and stuff like that, talking about pressure, volume, temperature, and how they're all related. As we mentioned, pressure is defined as the amount of force exerted on the walls of a container, okay? Pressure is annoying, has like 17 different units. The ones you may see are these: ATM, atmospheres. kPa is kilopascals. That is our SI unit for pressure. It's derived from the joule. Energy is joules. It's derived from that, so we use that one mainly in physics, but we use it a little bit here as well. Millimeters of mercury has like medical applications. Used to be how we tested like blood pressure and stuff historically, so we still use that for blood pressure and stuff. And torr is like torrential pressure for like rain, weather, water pressure, things along those lines. They're all just different units of pressure, and you can relate them to each other using this expression. 1 ATM is the same as 101.3 kPas, which is the same as 760 millimeters of mercury, which is the same as 760 torr. So if I give you 1 unit of pressure, you can use those expressions to convert between them if necessary. Now, all these units work the same way. Pressure is simply a measure of how much force is exerted over an area. All right, so here we have the word force and pressure, their definitions. The force this book exerts on your hand is just the weight of the book itself. Okay? So holding a book in your hand like that would exert a certain force. Now, pressure is that force per unit area. So how much force for a small area? And you kind of see their example they use here. If you balance this book on a pencil, first of all, you're very skilled. Second of all, that's going to hurt a lot more, right? You have all that weight concentrated into a small area, applying a very high pressure. Okay, the area being applied by this first example is your entire hand. That force spreads out over a larger distance, therefore there's less pressure. In B, you have all that force concentrated into a small area, therefore there's more pressure. So pressure is how much force is exerted and over what area. We're going to talk about volume, pressure, and temperature and the ways that they're related to each other. They all are mathematically related to each other. Some of them are directly proportional, meaning when one goes up, the other goes up just the same. And some of them are inversely proportional, meaning when one goes up, another goes down. Okay, so here is how temperature affects the other two. As temperature increases, if this happens in a rigid container, meaning a container that is like a solid, it doesn't change its shape. Like imagine like a propane tank, right? It is rigid. It's not going to change into a different shape. So if you increase the temperature inside that propane tank, the pressure increases as well. The molecules inside the propane tank are moving faster, and when they hit the sides of the container, hit it with more force. So increasing the temperature directly increases the force, right? Which increases the pressure. Now, if you increase the temperature of a flexible container, something like a balloon can expand or contract as needed. So increasing the temperature of a flexible container will increase the volume, right? It'll start to spread out to try to maintain the pressure the same. Okay, as you increase the temperature of like a balloon or something, the molecules start moving around faster. They hit more of the walls harder, applying more pressure, but now that the container can move, the container is just going to stretch out to try to balance it out. If you have a balloon and you leave it in a really hot car, it's likely to pop for a couple of reasons. One, if it touches the side of a really hot window or something, it'll pop. But even if it's perfectly just floating in the middle of the car, it'll still potentially pop because the hot air inside the car is making the gases move faster and stretch out the balloon. And if it stretches too far, it'll pop. The opposite's true if you take a balloon and like shove it in the freezer. The gas molecules will start moving slower and you'll actually see the balloon shrink down a bit. So temperature can either increase pressure or volume depending on your container. If your container doesn't change shape, it's just going to increase the pressure. This would happen like in your tires or in like a propane tank or a gas cylinder or like a classroom. That's not going to change its shape. A flexible container that allows the volume to change will increase the volume if the temperature goes up. As volume increases, meaning you're expanding your balloon, your container, whatever you're expanding, pressure goes down. And this is actually, you're not changing the force of anything. You're not changing the temperature. You're not changing the force of the particles, but you're just giving them more room. You're increasing the area, right? So like in our pencil example, we had a very small area hitting your hand. And basically all you're doing here is just instead of using a pencil, you're using just like a larger object, right? A larger object than a pencil, like maybe a fist, isn't going to hurt your hand as much. If you spread out the particles, there's less pressure because they hit the sides of the container less often. There's a larger force or a larger area that force is now dispersed through. We have our picture here. We have the same amount of particles, assumingly moving the same speed. Okay? But in the left one over here, the pressure is much lower. These particles are less likely to be currently hitting the walls because the walls are further apart. The same particles over here have a much higher pressure just because they're crammed in there. They're hitting the walls constantly. You can also choose to add more gas to your sample. This would mean like increasing the number of moles of gas. A flexible container will increase in size. So you will increase the volume of a flexible container like blowing up a balloon. Right? If you add more air to a balloon, it's going to get bigger. Okay? Increasing the pressure of a rigid container, adding more gas into a rigid object will increase its air pressure. So we do this if our tire pressure gets too low, you can add more air, right? Something along those lines. These two relationships can be summarized into our two gas laws. The one on the left you'll see all the time. It's written on your formula sheet. It's the main gas law called the ideal gas law. Pressure and volume is equal to the number of moles of gas times the gas constant times temperature. On the right, we have sort of a comparison. We have the pressure, volume, and temperature of a gas before something happens. So like an initial pressure, volume, and temperature. That's equal to the final pressure, volume, and temperature. Basically, it's saying your pressure, volume, and temperature are always proportional. And you'll have the same pressure, volume, and temperature afterwards, but more of it might be pressure, less of it will be volume. But the ratio of them will always be equal. The first one is called the ideal gas law. The ideal gas law is used to compare the pressure, volume, number of moles, and temperature of an ideal gas. An ideal gas is just a concept we use as a way to estimate what a gas's quantities really would be to make calculations much easier. Ideal gases don't exist in real life. No gases in real life are ideal, but most gases are like 95% ideal or 99% ideal or maybe 90% ideal. They're like really close to this, and this makes our life a lot easier than having to calculate every little minute detail of a gas. It's like in a physics problem, for example. If I want to calculate how fast I throw a baseball and how much force that has, I don't want to have to do annoying things like calculate the exact density of the air or calculate how much water content's in the air to like subtract that from the force, or to calculate like tiny little minute details like this. And the ideal gas law is essentially the same. We get 95% of the calculation right and do like 10 times less work. Now, those assumptions we're going to make specifically for the ideal gas law are that ideal gases don't actually take up any space at all. The gas molecules are essentially zero space. They take up no volume. And that's not true. Gas molecules, if you add up all the volumes of the gas molecules in the room you're in right now, they would take up some of the space of the room. And that would affect some of the calculations for pressure and temperature, because the volume would be a little bit lower than expected. But gases are really tiny, so they don't take up much space. Even when you add them all together, they're not taking up a ton of the space in the room, which is why that's a reasonable approximation to make. If you didn't make that approximation, you'd have to calculate the volume of all the different molecules, add them all together, and subtract that from your total volume, which sounds like a pain in the butt. The second approximation we make is that gases don't experience any sort of intermolecular forces for each other, which is also not true. We know that all things have London dispersion forces, so there's always some amount of attraction, even in a gas where they're moving so fast they hardly care about each other. They care about each other a little. A real gas, if you were to calculate like an actual gas's quantities, its pressure is going to be a little bit higher in math and a little bit lower in real life. The intermolecular forces that gases experience reduce their pressure just a little bit, but it'd be like 1% or 2%. And therefore, we don't really care, right? Gases experience very low IMFs as it is, so calculating all that just makes things a lot harder for us. Okay, the gas constant is used in this equation, and this is just a number, but its number actually has a couple different values you can use, and it just depends on which unit for pressure you have in your problem. The units for pressure aren't exactly equal to each other. So if you have ATM as your unit of pressure, you just use this number for R. If you have KPA, you use this number. If you have either of these other two, you use this number. These numbers are provided on your formula sheet for AP Chem, so it's not really anything you have to remember. You'll use the top two way more frequently. The second one is the one we used in the root mean square velocity formula earlier. This 8.31 or 8.314 is what we used in that problem. You'll use that one and you use this ATM one all the time. These other two, you'll probably never remember those. So the sort of problem we're going to use the ideal gas formula is something like this. I have a container with a volume of 4.5 liters. I have its volume. Pressure of 2 ATMs. What's the temperature of the gas if I have 0.38 or 368 moles of gas inside? So you'll be given 3 of these 4 quantities of a gas: pressure, volume, number of moles, and temperature. If you're given any 3 of them, you can solve the last one using the ideal gas law. Okay, so I'm going to write PV equals nRT. I'm going to plug in what I know from my problem. Pressure is given to me. It says it has a pressure of 2 ATMs. It says ATMs, I'll keep that in mind for when I write my R. Volume V is 4.5. Liters is the unit we want. It's already in liters. That's great. N is number of moles, given to us as 0.368. That's a 6, believe it or not. R is our gas constant. I used ATM for pressure. So if I go back here, ATM means my R's number will be 0.0821. 0.0821. T is my temperature. That's what I'm looking for. And now I just do some algebra. Solve for T. Simplify this. You get 9. The other one you can do in your head if you want. I'd use a calculator. 0.368 times 0.0821. 0.0302 something times T. Now I need to get this by itself. So I'm going to do 9 divided by 0.302. 0302. And I get a temperature 298. Your unit is Kelvin. Okay. If you solve a problem for temperature, it'll already be in Kelvin for you. Make sure if you're solving a problem using this formula and you're using temperature, make sure you put it in Kelvin first. The R, the gas constant, is already set up to be in Kelvin, to give you Kelvin when you get your final answer. So 298 Kelvin would be my answer there. My second example, what's the pressure of a 450 liter room with 5.6 moles of oxygen gas at 292 Kelvin? Okay. So again, we have PV equals nRT. I'm given 3 of these 4 quantities. I'm going to plug in what I know. Pressure is unknown, so I'm going to leave that as P. Volume is 450 liters. N is your number of moles, 5.6. R, we have 3 different values of R, and it doesn't tell us specifically which pressure we need, so we can use any of them. I'm going to use this 0.0821 because that one's used most frequently, and that will make my unit ATM for pressure. Temperature is 292. It's already in Kelvin for me, so I don't need to change anything. If it gives you something in Celsius, say it gave you like 10 degrees Celsius, you just add 273 to turn it into Kelvin. But this time it's already in Kelvin, so let's not do that. Okay, I have a variable to solve for. Just let's do that. Pressure times 450 equals a bunch of numbers. Let's multiply them all together. 5.6 times 0.0821 times 292 is 134. I'm just going to round that to like 0.25. Get pressure by itself, divide by 450. I get 0.298 ATMs. If you would have chosen a different R, you would have gotten a different number. You would have gotten 30.2, but if you used 8.31 as your R, you would have got 30.2 kPa. And you would have gotten a different answer if you used that third one as well. But these are equivalent. They mean the same thing. So either answer is good. All right, lastly, we have just kind of minute little detail here. We have an abbreviation, STP, that stands for Standard Temperature and Pressure. You might see this in a problem. It'll say like you have a gas at STP. So it just says standard temperature and pressure. And what that means is your pressure is 1 atm is what we use. And your temperature will be either 0 Celsius or 273 Kelvin. They mean the same thing. So it's just giving you two of your quantities for free. 273 Kelvin, 1 atm. Okay. So it'll make a question look really short. At STP, which tells you your temperature and pressure, how many liters, what volume, are in a 1 mole of helium gas? So PVA equals nRT. P isn't giving me directly, but it's standard pressure, which means pressure is 1. V is my volume. That's what I'm looking for. Number of moles is 1. R, I used ATM, so I must use 0.0821. Temperature is standard as well, so I'll put 273. The left just becomes V. Multiply all this together on the right, you get 22.4 liters. This is actually technically another definition of what a mole is. If you notice in the problem, I'm looking at exactly 1 mole of gas. 1 mole of gas, by definition, at standard temperature and pressure, has a volume of 22.4 liters. So there's a couple definitions of moles, like a mole is 6.022 times 10 to the whatever, That is one definition of a mole. This is actually another one. 1 mole of gas has a volume of 22.4 liters at standard temperature and pressure. I have 48 grams of carbon dioxide in a 22.4 liter container. Is the container at STP? So here's just a little bit more challenging way to sort of ask the same question. 48 grams of CO2. Now, grams doesn't really do anything for me, as usual, but I can convert this to moles easily doing some train track stuff. Grams of CO2 to cancel. Moles of CO2 on top. 1 mole of CO2 weighs, so it'd be 12 plus 32 is 44. 48 divided by 44, so 12 over 11, 1.09 volts of CO2. Okay, now is this container at STP? Let's just check to see if the math works out. So at STP, we could solve the gas law. Okay, pressure should be 1. It says it's a 22.4 liter container in my problem. Number of moles, we'll kind of solve for what that should be. R is 0.0821. And 273 is my temperature. This will tell me how many moles I should have at standard pressure and temperature, and it should match up here. So I get 22.4 equals 0.0821 times 273 is 22.4 N. Divide each side by 22.4. 1 equals N. So if it's under standard temperature and pressure, that means I would have 1 mole, but I actually have more than that. So the answer is no. I'm not at standard temperature and pressure. Otherwise, I would have gotten this as my answer to my problem. That's kind of a weird little application you can do. Okay, we had 2 different ways to find the moles, and we just wanted to see if they matched or not. The second equation is the combined gas law. Now, this is used to calculate pressure, volume, and temperature before or after some sort of change occurs. So P1 V1 over T1 equals P2V2 over T2. You'll actually see three different equations that look very similar to this, called like Boyle's law and Charles' law, and a couple of other ones. This is called the combined gas law because it just combines all of them into one. It simplifies it a good bit. And what you can do is if there's any quantity that's held constant in your problem, say like this change occurred at constant temperature, you could just get rid of temperature on both sides. It would be the same number anyways, so they would cancel out mathematically. If they both happened at 10 atms of pressure, you have a 10 on both sides, so you just cancel them out. So if anything is held constant, even if it doesn't give you specific numbers in the problem, you can just get rid of it. Okay, we have an example here. It says a weather balloon containing 1850 liters of helium gas at 23 degrees Celsius and 765 torr. Torr's weird, but it's a unit of pressure. Is launched into the atmosphere. The balloon travels for 2 hours before bursting at an altitude of 32 kilometers. Who cares about that, how long it took to burst or how many kilometers it's at? But we now know its new temperature is negative 44 degrees Celsius and the pressure is 6.51. So right before bursting, this is my temperature and pressure of my balloon. And I want to know what's the volume of the balloon just before it burst. Okay, so I could recognize this as a combined gas law problem because I have multiple pressure, volumes, and temperature. Some sort of change is occurring. In this example, the change is the balloon's going up in the atmosphere, and its pressure, volume, and temperature change as its altitude changes and the temperature of the air changes. Okay, so I have my combined gas law this time, and I'm just going to plug in all the information I have. All of my initial conditions I'll plug over here on the left side. So my initial pressure was 765. My initial volume was 1850. Divided by my initial temperature was 23 Celsius. Now I'm not going to use Celsius. I'm going to add 273 to that. All right, I got 296 Kelvin. Always make sure to use Kelvin, even in this formula as well. Otherwise, your answer will be wrong. My pressure 2, volume 2, and temperature are after my change occurred. So this is after the balloon travels for 2 hours, right before it burst. Its new pressure is 6.51. So its pressure went down a whole lot. Its new volume, we don't know. That's what we're looking for. The volume of the balloon just before it burst. And the new temperature is negative 44 degrees Celsius. Okay, so we have to add 273 to that. So negative 44 plus 273 equals 229 Kelvin. If we put in the Celsius and had a negative number here, our final answer for volume would have been negative. And nothing can have a negative volume. So that's why it's important to switch to Kelvin. All right, so we have just one variable to solve for, get it by itself, and that is our problem. You can solve this like a traditional proportional where you cross multiply, set the sides equal to each other. But we don't have to do this super mathematically. We have a bunch of numbers, so we can just simplify them. So I'm just going to multiply and divide this left side to simplify it. 765 times 1850 divided by 296 equals 4781.25 on the left. That's a lot easier to work with than all three numbers. On the right side, I'm going to simplify these two numbers. I can't do anything with my V2, but I can do 6.51 divide by 229. And I get 0.028427 yada yada times V2. Now to get V2 by itself, I just have to divide by this number. So I'll divide both sides by 0.028427, whatever. And I end up with 4781.25 divide by this small decimal. And I get this really large number. I'm just going to round it to the first three digits, 3 sig figs, so I'm doing 168. The rest of that just rounds down. So instead of writing all the digits, I can just write it out like this. So my balloon got really, really large right before it exploded, which kind of makes sense, right? The balloon got really, really big and then blew up. We use this equation whenever we have like a before and after sort of situation. The tricky thing about this one is it's not actually given to you on your formula sheet, so it's one you kind of have to know. They want you to know the relationships between pressure, volume, and temperature. So you have PV over T equals PV over T. But if you kind of think about it, that makes sense. If you go back to the ideal gas law, right, you already have PV on the same side for that equation too. So to talk about temperature, you'd have to divide by T. So you can just rearrange this equation a little bit to be PV over T equals NR. And then it kind of matches here. So PV over T, it's just important to remember the right sort of order there. Okay, so an ideal gas, as we said, is one that has no intermolecular forces and takes up no volume. Nothing in real life is exactly this. The real gases that are the most ideal, though, are going to be the ones that minimize these approximations. Small molecules are pretty ideal because they have a smaller volume. So the smaller something is, the more ideal it is. Because of this, helium is actually super ideal because it's really, really tiny. Molecules with less intermolecular forces are also more ideal because they don't interact with each other as much. So to get the most ideal gas you can get, you want it to be small and you want it to have the lowest intermolecular forces possible. And we're really worried about London dispersion forces. So we want them to have zero or as close to zero London dispersion forces as we can. So if we look at our periodic table, helium, at the top right, is the smallest, has the lowest mass, and it is the smallest atom, has the smallest atomic radius because it's the furthest up and to the right, and it's a noble gas, so it has very little intermolecular forces. So it is the best approximation of a ideal gas. When particles are moving faster, they interact with each other less. Therefore, if you increase the temperature of something, it's going to be more ideal. The faster the things are moving, the less they care about each other. Okay? When particles bounce off walls, they interact with them. IMF is also bad. Molecules with lower pressure, then, are more ideal. So the more the things are hitting the walls, the more they're going to be thrown off by being a real gas and not ideal. So the most ideal gas possible would be helium. That's moving really, really fast, so it doesn't care about its friends, but also is in just a gigantic room, so it's not bouncing off the walls and has a low pressure. So you can imagine like a single helium atom traveling in the atmosphere super, super fast is really, really, really good at being an ideal gas. It's minimizing the approximations we have to take. We have these three examples. Which of the following gases are the most ideal? Oxygen, nitrogen, and fluorine. Okay, so what we're going to look at in this example is just how big the gases are. The smaller they are, the more ideal they are. So pull up my periodic table. We have, what do we have? We have N, O, and F. We have this sort of top right corner, N, O, and F. So we have to remember our periodic trends a little bit here, but things get smaller as they go up and to the right. N, nitrogen, oxygen, and fluorine, all of them are going to be non-polar, right? Because you just have an N bonded to itself, an O bonded to itself, or an F bonded to itself. So all their intermolecular forces should be the same in that situation. But fluorine atoms, even though they're heavier, they're further to the right, they have a greater effective nuclear charge, and they are smaller. Fluorine is the smallest, has the smallest electron cloud too, which means it'll have the least London dispersion forces. Okay. For both those reasons, fluorine F2 gas is more ideal than the other two. Okay. It's smaller, has less intermolecular forces. And that's all you'd have to do. Ideal gases don't interact with each other. If you have two ideal gases in a mixture, the total pressure is just equal to the partial pressure of each. And all that means is, if you have an example like this, I have some oxygen gas over here, and I have some nitrogen gas. If I just mix those together, you just add their pressures together. The pressure of this oxygen is 159. The nitrogen is 573. So if you combine these two containers into one, you just add together their pressures. It doesn't matter what your molecule is because they're not interacting with each other anyways. Pressure only cares about how many total molecules you have over what space. So combining these two things together just increases the pressure, like you just take the sum of the pressures. I have a mixture of ideal neon and ideal hydrogen gases. The neon has a partial pressure of 1.2. The hydrogen has a partial pressure of 0.4. What's the total pressure of the gas? It's pretty simple. All you have to do is add 1.2 to 0.4. You get 1.6. So I'm not even going to show you the math on that. It's very simple. If you have multiple pressures, you just add them together to get the final pressure. Right? There can also be more than two. You can have dozens of different gases. And the general formula for partial pressure is just add them all together. This is a formula I'm supposed to give you, but it kind of just makes sense. The total pressure equals pressure 1 plus pressure 2 plus pressure 3, and so on. Now, a little bit more complex, the same thing also applies for moles of gas that you have in a system. The total moles of a gas in a system will equal to the partial moles of each gas in the system. Right? In an ideal gas, there's no interaction, so it doesn't matter which moles are what. The total number of moles of gas in a sample, you just add together all the different kinds of gas. So if you have 1 mole of argon and 1 mole of neon, that's just 2 total moles. It doesn't matter that one's argon or one's neon. It's not going to act any differently. I have 10 moles of nitrogen, 8 moles of argon, and 4 moles of xenon. How many total moles do I have? 10 plus 8 plus 4 equals 22. And that's it. All right. So that is gases. We have a couple of important things. Let me pull back up at the beginning here. Okay. So knowing the two gas laws is really important. Calculating problems using the ideal gas law and combined gas law is what we're going to be mainly focusing on in class. Calculating, there'll be lots of multiple choice questions involving the kinetic molecular theory. What happens when I increase the temperature? What happens when I decrease the molar mass of this gas? And then there'll be some multiple choice questions with the Maxwell-Boltzmann distribution. So there's a lot of interesting conceptual questions that they'll talk about a lot in this chapter. And there's a lot of math formulas we need to solve as well. So it's a good balance of math and kind of having some concepts straight in your head. And we'll be practicing those things in class. All right. Thank you for watching, everybody. Have a great day.